I'd like to welcome you again to HI-TEC, another conference day. We've got lots going on today. This morning, I want to take a minute to thank CORD, the organization that did all the legwork for us. Sheila Wilson and David, I'm looking for David, he's in his chair over there, and Timus, who was at the registration and helped us with the exhibits. They really made all the details come together for this conference, and I think it's all gone really smoothly, so I'd like to give them a round of applause. And I know I wouldn't be still standing if they weren't, if they hadn't been doing some work.
As the world moves into the 21st century, there are few people who have not been affected by the laser, that mysterious device that has become so common in our modern popular culture. Although there are now lasers that begin to approach the power levels of those portrayed in science fiction, lasers find the most use as tools in thousands of applications, some of which you may have never imagined. Lasers is in the field of communications. In the 1980s, telecommunication systems began to move away from copper wires in favor of fiber optics, all of the high-speed communications traffic on long-haul fiber optic networks. Lasers are used because their high-intensity beams can travel for hundreds of kilometers along an optical fiber without the need for amplification. Interesting uses of lasers are in materials processing. There is something about a beam of light cutting through steel that fascinates almost everyone, possibly because it is so close to the image of lasers we see in science fiction. High-power lasers are a mainstay of modern industrial manufacturing. Chief among them is the carbon dioxide gas laser. The CO2 laser can be designed to provide beam powers of a few watts to tens of thousands of watts. Lasers can provide some distinct advantages over other methods. Lasers produce smooth, clean cuts, unlike cutting torches. The heat applied to a metal workpiece is sharply focused, so it affects only a small area around the cut. With a cutting torch, the heat-affected zone is larger. The metal in the heat-affected zone becomes more brittle than the rest of the workpiece, so in many applications such as aircraft parts, the heat-affected metal must be removed by grinding. This results in longer manufacturing times, higher costs, and reduced accuracy. With the laser, the cut is very smooth, and the heat-affected zone around the cut is very small, so grinding is kept to a minimum. In some cases, cuts are so smooth that no grinding is required. In this example, a 1200 watt CO2 laser is cutting parts from a steel sheet 1/2 inch thick. The shaft is heat treated by the beam from a 15,000 watt CO2 laser. Traditional methods using torches or furnaces waste energy and can take hours, but the laser completes the task in only a few seconds. Car manufacturers make extensive use of lasers to harden transmission gear surfaces for a long and reliable service life. Laser, the precision required for micromachining. In this example, a tiny gear, only 300 microns in diameter, is being cut from Pyrex glass by the beam from an excimer laser. The next generation of supermachines will operate in a microscopic world, bringing enormous advances to science, electronics, and important uses of lasers come in the field of medicine. The infrared beam from carbon dioxide lasers is heavily absorbed by the water in human tissue, making it an excellent cutting tool for the surgeon. The heat of the beam cauterizes tissue as it cuts, resulting in almost bloodless surgery. CO2 lasers can be used to seal cuts from conventional surgical procedures. It is also used to remove scars and other skin lesions with up to 50 watts of power, allowing this type of laser to be exploited for its heating effects as well as for its wavelength. The retina of the eye is more sensitive to green light than any other color, making the argon laser a perfect choice for many types of eye surgery. Detached retinas cause blindness in thousands of people each year, but if caught early, a pulsed argon laser may be used to weld the retina back in place before permanent damage results. Today, a surgical technique that is gaining popularity is laser vision correction, or LASIK. In less than 15 minutes, this procedure can greatly reduce a patient's reliance on corrective eyeglasses. In some cases after surgery, eyeglasses will no longer be required. The surgeon first uses a high-precision instrument to separate the layers of corneal tissue and create a thin flap on the surface of the eye. This flap is folded back, and the ultraviolet beam from an excimer laser is guided to gently reshape the underlying tissue. The cornea's new shape is what improves vision. After reshaping is complete, the flap is replaced, and the patient can resume most normal activities within 24 hours. Applications of lasers have long been touted by science fiction writers, who have attributed almost magical qualities to this practical tool. However, the military have long used lasers for tasks like pointing, aiming, and the guiding of munitions to their targets. But today, serious work is being done to use the highest power lasers directly as weapons, most notably to destroy approaching gear. The infrared beam from a chemical laser is directed on a dummy missile casing. Although invisible to the camera, the tremendous power of the laser beam causes the casing to explode. We live in the world of a photon, with optical and electro-optical technologies on the cutting edge. Students today are more aware of science and technology than ever before, and have a keen interest in learning and getting involved. And their diligence will pay off. There are thousands of rewarding careers that involve working with all types of lasers. In telecommunications, for example, careers range from the technicians who install and maintain the fiber optic infrastructure, all the way up to the visionaries who make their dreams of new and exciting applications a reality. It isn't just scientists that use or interact with lasers. It is every one of us. Lasers and laser-based products have become common in every area of human endeavor. Every time you pick up the telephone, watch a movie or TV, use the internet, or just carry on your daily life, you benefit from the laser.
Good morning. I'm Dan Hull. There's an exhibit that's forming outside. You saw part of it while you were getting your food this morning. There's a button in that exhibit that you may have seen that says, "Oh, laser scientists never die. They just become incoherent." I'm an old laser scientist. And we have another one here that, before I introduce our speaker, he's not quite as old as I am. MJ Swallow, the provost at the University of Central Florida, who set up the Creole Institute, is back there. Wave your hand, MJ. They're bringing some exhibits this morning too, so we really appreciate him. And he's not incoherent either. But old scientists sometimes tell a story, and if you listen to Story Musgrave yesterday, you really understand that very well. I have one. In May 1961, I was a fledgling young electrical engineer working at the Westinghouse Defense Center near the Baltimore airport. I was trying to develop timing circuits for some defense radars, and I wasn't enjoying things very much. I was trying to figure out why in the world I had brought my young wife all the way up from Texas to this alien land where we didn't know very many people, we were away from our family, and we could not eat Mexican food. Just before lunch, my boss came by and he said, "Read this Scientific American article. Bell Labs has built the first helium neon laser, and we want to build a second one." Well, you know, I really didn't understand what a laser was or what it was good for, but I really didn't want to build timing circuits anymore. So I came back and said, why not? And so I got to start on the beginning of the most incredible opportunity in a career anyone could have. I was in there very early. I wasn't the first one, but I was like the second one in a number of things. We finished that helium neon laser. We went on and built a ruby laser, and we focused it down and we blew some holes in a razor blade, and some other people did, and the Department of Defense went nuts. And money for research and development of lasers started flowing like water. And because everybody said, this is the device we're going to be able to shoot down the ICBMs and save the world from the Russians. Well, we worked on that a long time. In 1963, Premier Nikita Khrushchev came to the United Nations, and he, after banging his shoe on the podium, he raised a ruler up and he said, "See this laser shot in this ruler? We're going to be able to rule the world." By that time, we already knew that it would have been much easier to throw the laser at the ICBM than it would be to shoot it down. But lasers have progressed a long time since then. And although there are some incredibly good examples of applications in the defense industry. You'll see some of those this morning, I'm sure. Lasers have been bringing forth applications in other areas that have made our lives much better and much easier, and our country much safer. 2010 marks the 50th year of the laser. The first lasers made operational by Maiman in 1960, and so we're in this year. And the professional societies, the Optical Society, the SPIE, the IEEE, and HI-TEC and others have joined together in something called Laser Fest. And it's a series of celebrations that are going on all over the country. It's really all over the world this year in different places. The first one occurred in February the 12th at the Smithsonian Institute in Washington, and there were over 9 or 10 Nobel laureates that were there. And so this is a Laser Fest celebration today, and that's why you see these banners, you see these signs, and you see what we're doing. We are particularly fortunate today to see someone who represents what I consider a newer generation of laser leadership. I'm delighted to be able to introduce to you today a keynote speaker, Dr. Anthony Johnson. He's the director of the Center for Advanced Studies in Photonics Research at the University of Maryland in Baltimore County. In your program, there's a lot written about him on page 47. There's a lot more that you'll see on the screen. I'm not going to say it all, but I want to tell you he's done a lot of things. 70 refereed publications in this area, chapters and books. He has 4 patents. He's on the board of directors of the American Physical Society, the IEEE, the OSA. In 2002, he became the first African-American president of the Optical Society of America. And in 1994, he was nominated as the Outstanding Black Engineer of the Year. And he's a fellow in the American Association for the Advancement of Science and a lot of other areas. He's got accolades I could spend a lot of time on, but I won't. In addition to his technical achievements, Anthony is one of the outstanding leaders in this country to encourage minorities to enter science and engineering and technology. And I've asked him sometime during his presentation this morning if he would share with us for 10 or 15 minutes some of the experiences and the things that he has working where he's encouraging minorities to do this. So without talking any more, let me introduce to you Dr. Anthony Johnson.
Good morning, everyone. Thank you, Dan, for that very nice introduction. It is quite a pleasure to be here at HI-TEC. Let me warn you, though, that I'm really a lab rat. I'm a hardcore bench scientist, and this is quite a different venue for me. I'm much more comfortable talking about research that my group is doing in ultra-fast phenomena, looking at nanoscale materials, but this is an interesting audience, and it's a pleasure to say some things about the 50th anniversary of the laser. And I hope to give you some flavor of the history. I think the biggest issue with giving this presentation is that lasers are so prevalent is trying to decide what not to put into the talk. And so a little bit about the history, some of its uses, wide-scale uses, and as Dan mentioned, he was also wanted me to spend a little time talking about another passion of mine in addition to research, and that is trying to open up the field, or do what I can to open up the field of science to minorities and women into the field, which I've been doing for quite a while. So without further ado, let's see if we can get all this to work. The laser, as many of you know, is an acronym for light amplification by stimulated emission of radiation. And this is the 50th anniversary, and the first working laser was generated by Ted Maiman at Hughes Research Laboratories on May 16th, 1960. And this was done with ruby, a very difficult material to actually generate the first laser. But indeed, he was quite successful in his endeavor to do that. And they had quite a bit of competition also. And one of the things that is you will have heard, perhaps, is that when it was invented, it was called a solution in search of a problem. No one knew what to do with it at first. And now you can't get away from it. So again, a solution in search of a problem. And there are so many uses, and I'm just going to highlight just a few of them right now that we nearly take for granted. You have the laser printer is one, the barcode scanner that everyone has used in the grocery store to scan the barcode and get that information about what the product is, and of course the CD player, one of the early uses of the laser. And here's one that we're not that pleased about, and that is the laser radar to detect the velocity of vehicles. And then actually it is used in laser hair removal and also for eye surgery, to correct the cornea in particular. Now, one of the interesting things about the laser is that the initial thought about light emission, and one of the key components, was actually thought about by Einstein in 1970, and that's the concept of stimulated emission. And so, again, 43 years before the first demonstration, Einstein predicted this. And of course, Einstein is a very unusual and very brilliant person. Talked about this process in which one can consider an atom, and you consider an atom in having simply just two states, a ground state and an excited state. The concept of stimulated emission is a photon with energy h nu, where h is Planck's constant, nu is the frequency. When it hits this atom, it actually stimulates the emission of a photon by de-exciting this excited atom back to the ground state. But what's neat about it is that these photons, then the second photon that comes out along with the first one, has the same frequency, the same phase, polarization, and direction. And a laser is basically a cascading of this process in which electrons are excited and forced to emit irradiation in this very fine laser beam. But again, the thoughts were early on. And physicist Charles Townes, whose name is most associated with the laser, wanted to take this concept of stimulated emission and produce powerful microwaves from a molecular medium held in a cavity, and therefore produce a maser, microwave amplification by stimulated emission of radiation. The maser, which preceded the optical version of that, or the laser. And now Charles Townes, who recently celebrated his 90th birthday, is still very active, and has been giving, and particularly in this LaserFest year, has given a number of talks about the ideas of the laser. So in 1948, he joined, at the age of 32, he joined Columbia University as an associate professor with a remarkable salary of $6,000. Remember when that was something? Now, Columbia is world renowned for the number of Nobel laureates. There are 20 there, including Charles Townes at the time. And his department head at that time was Isidore Rabi, very well-known physicist. And the Columbia Radiation Lab had a secure source of support, a block grant from the Joint Services of the Army, Navy, and the Air Force. And so there was lots of funding for research at Columbia. And radar, and he was quite interested in radar, was developed by scientists, and this was important for winning World War II, and as we know, the atomic bomb ended the war. So, as Charles Townes says, one day an Army representative came around shortly after the end of the war and asked of the department, headed by Rabi, would you be willing to keep this lab going and do some physics with it? And we can give you some money, something like $500,000 a year. And Robbie was very impressed with this generous offer, so much so that he told them half of that amount would be too much. And so, of course, they obliged him by reducing the amount. Here's a picture of President Eisenhower and Professor Robbie at Columbia. And in 1953, after the war, Dwight Eisenhower arrived in the White House, and he began to cut military research spending. So Robbie had to cut the molecular oscillator project that Charles Towns was working on to try to make the maser. So in '54, Robbie and Kutch, another Nobel Prize winner, marched into Towns' office and said, look, you should stop the work you are doing. It isn't going to work. You know it's not going to work. We know it's not going to work. You're wasting money. Just stop it. And Charles Towns said, I was so thankful that I had tenure. I heard this is incredible. So he may not have made that process without having tenure so that he could just continue to do his research. And so fortunately he had tenure. That's a wonderful story that Charlie tells. The invention of the maser, Charles Towns. Now this is a very famous picture of Charles Towns and his graduate student, Jim Gordon. And this is really hard for me to see Jim Gordon here. Jim Gordon we were together at Bell Labs, and this is such a distinguished scientist. It's hard for me to think of him ever as a graduate student, but he was. But I got to work with him at Bell Labs. And so what happened is that during a seminar in early April of 1943, 3 years after he made the notes, Jim Gordon burst into the seminar basically saying it was working. The maser was working. The masers were the first device to use stimulated emission to amplify photons to make, in the case of microwaves. And it basically was a two-level gaseous. Ammonia was used as the medium to do this. And here you have this famous picture in front of their maser, Charles and Jim Gordon. This was the second ammonia maser, which had a wavelength of 1.25 centimeters. These are very long wavelength devices, microwaves. And here we have a picture of Prokhorov and Bazov, who were simultaneously thinking about microwave amplification as well in the Soviet Union. And here you have a picture of at a conference in 1958 with Gordon, Bazov, and Prokhorov. Another graduate student, Herbert Ziegler, as well as Charles Towns. And here is when Charlie Towns actually visited the Soviet Union to look at their maser work. And eventually, these three received the Nobel Prize for the idea of the maser, Towns, Bazov, and Prokhorov. Now, interesting enough, Charles Towns was a very generous person, and he noted the progress that was being made. And he says in his book, How the Laser Happened, that Prokhorov and Bazov are gentlemen and good scientists. It seems quite clear to me that the important concepts behind the maser had been coming together independently in Russia. And so the three of them were awarded the Nobel Prize. And as you can see from the timelines, that indeed there was quite a bit of overlap in the ideas behind the maser. So here is another Nobel Prize winner, a future Nobel Prize winner, Art Shallow, who happened to be the son-in-law of Charles Towns. And together, they had this famous paper on infrared and optical masers. At the time, the term laser had not been coined yet. That was actually coined by another graduate student, Gordon Gould, who was at Columbia as well. And instead of calling it an optical maser, he called it a laser. But this is the classic paper that has all of the theory necessary to actually build the first laser. And this is actually a picture of Gordon Gould, who was a grad student who indeed coined that term. And this is Art Shallow. And this is one of his favorite famous photograph, he had quite a sense of humor. And so here he is having an infrared laser, diode laser, as a so-called ray gun. And he has this special balloon. And inside the balloon is a darker balloon of Mickey Mouse and an outer balloon. And he would actually shine this infrared, therefore invisible laser into the balloon, and the inner balloon would pop because it would absorb the infrared light and not the clear outer one. And so that would just amaze students and kids. And but notice his face, the smile on his face. He loved this stuff. But he really had a great sense of humor. And it was at a meeting at the University of Michigan, in one of the sessions chaired by Art Shallow, in which Gordon Gould titled the talk "Laser: Light Amplification by Stimulated Emission or Radiation," and that's the coined the term. But Shallow, being mischievous as usual, said the laser was likely to be used mainly as an oscillator, not an amplifier, generating light rather than as an amplifier. And they basically mocked it and called it loser, light oscillation by stimulated emission of radiation. And of course, he brought the house down when he did that. But this would be typical of Art Shallow. Now here's the so-called first working laser. And I say so-called because this picture is not the picture of the first laser. This was the picture that his management at Hughes wanted to be in front of him. The actual laser that Ted Maiman made was much smaller, but it didn't have the pizzazz and that the PR folks at Hughes Research wanted. So this is a lot larger than the actual laser itself. And so this shows basically the reflector. There's a small ruby rod in here, and this is the output of the laser. But the actual here again, the head of Hughes, the public relations, complained that it looks like something a plumber made, and so they've therefore found a larger flash lamp that was used to pump the laser, and stuck this in front of poor Ted's face and took the picture. And this is the picture that is circulated over and over and over again, but it isn't actually the real laser, the first laser. This is a later picture of Ted Maiman, in which he is actually holding the actual laser. And so the PR folks thought this was just too tiny to be the first laser. So now another interesting story about the maser, about the optical maser of the laser, is that it was rejected by phys rev letters. And turns out that Samuel Goudsmith, another Nobel Prize winner, was the editor of phys rev letters, and he was headquarters at Brookhaven National Lab. And after the maser was invented, there were so many papers on masers that he basically had a general rule that he said, I'm not going to accept any more papers on masers. And unfortunately, he didn't actually read the paper to know that this was an optical maser. And he just basically assumed it was another maser paper and immediately rejected it. And so the paper eventually was accepted by the British journal Nature. And that is the first publication of the optical maser or laser. So PRL really missed an opportunity there. Now the second laser. This was produced by Peter Sorokin and Marek Stevenson at IBM. And this was a uranium-doped calcium fluoride laser that operated in the infrared at 2.5 microns. And the first true 4-level laser. Ruby was a 3-level laser. And so because of the rejection of Maiman's paper by phys rev letters, Sorokin and Stevenson actually drove out to Brookhaven National Labs on Long Island, where Sam Goudsmith was, and told Sam Goudsmith that they wanted a decision before they left. And so this raised quite a ruckus, and afraid of a parade of eager scientists personally delivering their latest achievements, Goudsmith told them, next time, tell your people from IBM not to come down here with machine guns. So they literally threatened him that he had to accept this. I mean, this was at this point, the second actual working optical maser or laser. And the next laser was the helium neon laser. And this was Ollie Javon Bennett and Harriet at Bell Labs made the helium neon laser. And this was after a 3-year effort to produce this, and quite a bit of money, $1 million to do this. And it was the 4th laser ever made, and this was a CW gas laser powered by electricity rather than light. And this is the laser that most elementary physics labs have, the red laser at 632 nanometers is a classic in most laboratories. And this worked on a different principle in that, with the helium neon, in that you actually excite helium atoms, and that excitation gets excited to the neon, which then lasers at 3 major lines, 3.39, 6328 nanometers in the visible, and at 1.15. So 2 infrared lines and 1 visible line. But this is a standard mainstay in most laboratories, the helium neon laser. And then the death ray. When Ted Mayman created this laser and had the working laser, he had quite a bit of stir about what was actually created. And so the the Los Angeles Herald had 2-inch red type titled on the front page, "LA Man Discovers Science Fiction Death Ray." A Pasadena newspaper headline, "Death Ray Possibilities Probed by Scientists." And another paper, "An LA man invents light brighter than the sun. Laser-equipped satellites could rule the Earth." And so this is what was happening at least in the publications at this time with the invention of the laser. And more science fiction. So we have these major things as well. Again, death rays, X-Men, and today, the Borg from Star Trek. So a lot of hype about lasers and what they could do at that time. Now, speaking of death rays, most recently in Scientific American, the July 19th issue, the U.S. Navy has a laser weapon that shoots down drones in a test. During a recent test, this was last May, a solid-state laser from the Navy, using a tracking system from Raytheon, shot down 4 unmanned aerial vehicles, usually known as UAVs. There is an unmanned drone. A solid-state laser is focused onto it, and with time, heating, fire, and it crashes into the ocean. You can see the outline of the wings of this drone. But this was taken down by a solid-state laser. This just happened this past May. Would you show that one more time? It's so short. So I think that we know that the military is working on very high-power laser systems, but I think the advance here is the tracking system, how to actually keep the laser on the drone. Now, there are no details. All they're willing to say is it's a solid-state laser. I suspect it's a very high-power neodymium YAG laser, but you can see that it is indeed capable of taking out a drone in this case, a UAV. So the idea of a death ray is maybe not as far-fetched, and the military is clearly working on it. Another high-power system, this is the National Ignition Facility, or NIF. In January of 2010, the National Nuclear Security Administration, or NNSA, announced that scientists at NIF, at Lawrence Livermore National Labs, have successfully delivered a historic level of laser energy, more than a megajoule, 1 million joules, to a target in a few billionths of a second, and demonstrated the target drive conditions required to achieve fusion ignition. This $3.5 billion stadium-sized NIF consists of 192 beams, each of which stands as the most energetic laser ever built. So primarily, this is the attempt to use lasers to create fusion. Now, the other approaches, of course, is to use magnetic confinement, typically a tokamak, but there's two major efforts going on to produce clean energy in the form of fusion. And I have a video here from NIF. This is about 3 minutes.
The universe, for billions of years, has been lit by the fire of countless stars. In these stellar cauldrons, hydrogen nuclei are fused together to form helium nuclei, releasing energy that lights the heavens. Can we build the technology to harness this awesome energy on Earth? As we approach our planet, that is exactly what's happening today. Far beneath these clouds lies the National Ignition Facility, located at Lawrence Livermore National Laboratory in Livermore, California. This facility has been built to bring star power to Earth. It is the world's largest and highest energy laser system. Containing 192 laser beams, NIF will explore controlled nuclear fusion to ensure global security, enable sustainable clean energy, and advance our understanding of the universe. 85 feet tall, the laser and target area building is the size of 3 football fields. Inside are 2 parallel laser bays, each containing 96 beam lines. In this animation, which is millions of times slower than real time, we will follow the process for creating a miniature star in the target chamber by riding along with some of the laser beams. The process starts by first energizing the laser amplifiers in the 2 laser bays by dumping electrical energy stored in capacitors into flash lamps. They convert the energy to light that is absorbed by the laser glass in the amplifiers. Later, when the laser pulses pass through the glass, they will extract this energy, thereby increasing the laser beam energy. Our trip with the laser beams begins in the master oscillator room, where a very low energy laser pulse is created. This pulse is only 20 billionths of a second long in duration, which is a beam of light about 20 feet long. It's amplified and then split into 48 laser pulses, which are carried over to the 2 laser bays using fiber optic cables. Here, the 48 pulses are amplified in a preamplifier by a factor of about 10 billion. Then they're split into 192 pulses and sent into the main laser system. As we track 8 of these beams through the facility, you can see the path of the beams highlighted in red. The first amplification occurs in the power amplifier. It has 5 glass slabs that were energized by the powerful flash lamps. Then they travel to the main laser cavity that directs the laser light back and forth 4 times through 11 sets of laser amplifier glass in the main amplifier system. This gives the laser beams another boost of energy. During this time, optical components ensure that the beams maintain their required pulse shape, quality, and spatial uniformity. On the final pass through the optical system, the laser light is allowed to exit and travel back through the beam lines and up to the power amplifier once more to pick up even more energy before heading down the long stretch to the switch yard. In total, the energy of the laser beams is increased a quadrillion times as they travel more than 1,500 meters from the master oscillator room to the target chamber. In the switch yard, the parallel bundles of beams are rearranged into a conical configuration. That's so they can be focused into the center of the target chamber and onto the target assembly. The assembly holds the spherical fuel pellet containing hydrogen. Here you see the 8 beams split into 2 groups of 4 beams each, one group traveling up and the other traveling down, heading for equidistant entry ports on the target chamber. Finally, the beams pass through the final optics assemblies, which convert the original infrared laser light to ultraviolet.
So, this has apparently been a very good start in the process of fusion, of laser fusion. And so, they're hoping to generate, I believe, 1.6 megajoules, and they've already demonstrated 1 megajoule, and they're ramping up slowly. And this looks very promising. All the reports I see are very hopeful that you may actually achieve ignition with this system. So now I'd like to say a little bit about how lasers have impacted the industry, the American economy and jobs and the like. And so what I have here is a report, again in honor of the 50th anniversary of the Laser Fest, that was generated by Tom Baer from Stanford University and the 2009 president of the Optical Society of America, OSA, and Fred Slachter from Lawrence Berkeley National Lab and from the American Physical Society, APS. They generated this report for OSTP, the Office of Science and Technology Policy, on contributions of lasers to American jobs and the American economy. And again, a laser, a solution looking for a problem, is a key technology which enables many major sectors of the economy, the U.S. economy, to exist. And laser devices are core technology for instruments performing vital functions in many industries, including transportation, healthcare, and telecommunications. So for example, the biotech healthcare sector is a $2.5 trillion industry. But lasers are an enabling technology. And so one has blood testing, sequencing, LASIK. This is a $20 billion industry. Diagnostic and surgical systems, $1.5 billion. And the core technology in this particular case are solid state and excimer lasers, and that's about a $400 million market just to sell those lasers. But again, this is a core technology that feeds into this $2.5 trillion healthcare. The other is transportation. It's a $1 trillion industry, and you have airplane, automobile manufacturing. This is a $500 billion industry. Cutting, drilling, welding, and that is a $5 billion industry, and the primary movers there are CO2 or copper, CO2 lasers there, and fiber lasers, and that's a $1.3 billion market. And then the telecommunications, e-commerce, and information technology, $4 trillion market. And there the main movers and shakers are diode lasers and fibers. And that's about a $3.2 billion industry. So again, at the core, as this is showing, lasers are really important enablers for these major industries to move forward. And so this was a report given to OSTP. I just picked out one of the reports. Now, this is not very easy to read, and I apologize for that. But among some of the medical devices that one is using lasers are medical or stents that are created using lasers to actually shape very unusual shapes for the stents. And we have a picture here of former President Bill Clinton, who actually had one of these stents inserted when he had a heart problem. Lasers are used for eye surgery. This is a photo of one of the gold medalists from China who had a detached retina, which was reattached using a laser. And then this talks about DNA sequencing and the advances that were made using lasers. Back in 1975, 2,000 base pairs per day were able to be sequenced, whereas today you're up to 2 billion base pairs per day using laser sequences. So this is a major advance, again, using lasers. And found a very interesting article on from photonics.com showing just how ubiquitous the laser is, that it is everywhere. And so the question is, can you avoid using a laser? So here we have a typical day for a typical citizen. So your alarm clock goes off, and if you can, you look over to the clock. You may be fumbling for glasses to try to figure out if that was a 7 or a 9, and you can go back to sleep. Now, if you have laser eye surgery, you may not have to go through this process. And an excimer laser generates UV light, which is used to modify the lens of the eye, thereby restoring vision to near perfect. Your next step may be to shave. And you may notice that metal blades have small dots on them. These are laser welding marks. The blades are welded on using neodymium YAG lasers at a rate of 100,000 spot welds per hour. And next, you may turn on your TV to watch the morning news. If you have a flat screen TV, more than likely a carbon dioxide or CO2 laser was used to cut the thin glass sheets that are an integral part of the picture transmission system. As you get dressed, even the clothes you wear have been produced with lasers. Many clothing manufacturers use CO2 lasers to cut the patterns and individual pieces of cloth for each garment before they are sewn together. And then you drive to work. Your car, many of the car manufacturers are using neodymium YAG lasers mounted on robotic arms to weld the entire car frames together, resulting in stronger and stiffer structures. And then in your car, the numbers on the speedometer or the snowflake on your air conditioning button were probably created using a marking laser. If you take the train to work, you're riding in a sheet metal showcase. The metal panels on the outside of the train were cut and possibly even welded using CO2 lasers. The seat supports, the bathroom fixtures were likely laser cut from stainless steel sheet metal. Lasers are also quite prevalent at the workplace. Surveyors and carpenters use laser levelers and measurement devices to find level surfaces and to quickly measure distances. Lasers are also quickly replacing traditional bubble levels and tape measures, improving the speed and accuracy using these tools. If you need a telephone or an internet for your job, you're definitely using lasers. The information superhighway and telephone networks are both made possible by semiconductor lasers that transmit light over fiber optic cables. These low power lasers emit short pulses of light at various wavelengths and enable transmission of information at nearly the speed of light throughout the world. The housing for your laptop was cut using lasers. Inside the housing, the processor, the microprocessors, and the memory chips were made using lasers. The red light emanating from your mouse is a laser. And if you need to print a document, you probably use a laser printer. And at the end of the day, you may retire to your entertainment center and look at a movie on your Blu-ray player. The blue light is used to read information from a disc. Blue is a smaller wavelength and therefore has much shorter wavelength than the older red light that was used for the old regular CVDs. Blu-rays can pack much more information into the disc and improves the picture quality dramatically. So again, this was just to show a typical day that you can't avoid lasers. They're everywhere, and we just take them for granted. And so whether we're actually using the laser or things that were made using a laser, the lasers are in everything. With the time I have left, I've been asked by Dan to say a little bit about diversity, recruitment, and some of the issues that I've been involved with over the years to to attract women and minorities into the sciences, and particularly optics. And it just so happens that 2 years ago, I was invited by the NSF. I have colleagues and friends in the Education Human Resources Directorate, EHR, as well as the Math Physics Directorate. And so I was invited to actually give a talk on this issue. And I'm going to show a few slides from this presentation. And I entitled it then, Photonics and Diversity, 30 Years of Experiences that I've had through the years. And one of the things that got me started in this field was actually spending a summer at Bell Labs. So in 1974, Bell Labs started the summer research program for women and minorities. And so this is 36 years ago, so I'm clearly 8 years old in this picture. Bell Labs had a very strong research organization, but there were very few women and minorities in this enterprise. And Bell Labs decided that in order to increase the number of women and minorities in the field, that perhaps they should start a summer program, an educational program within Bell Laboratories. And it was called the Bell Labs Summer Research Program for Women and Minorities, and it started in 1974. And I was a physics major at Polytechnic Institute of Brooklyn. And one of my physics professors heard about this program and suggested that I apply. And I applied the first year and was very fortunate to get in. And I had the choice of working with two people. I had the choice of working with David Austin on lasers and picosecond optoelectronics. Now, Dave Austin has gone on to do many things. He went on to become provost at Rice. He was president of Case Western Reserve, and then the immediate past president of the Kavli Institute out in Santa Barbara, which is a philanthropic organization, and he's at UC Santa Barbara. And then I had the opportunity to work with Bob Dines on low temperature physics. And he also went on and is a past president of the University of California system, and now is at University of California, San Diego. Couldn't have gone wrong with either choice, but I was interested in lasers, and they sounded interesting, and that's why I did my first summer. And Dave Austin was a wonderful mentor, and eventually he also became my thesis advisor. In that they also had a Bell Labs fellowship program for women and minorities as well, to go to any school of their choice, to pursue a doctorate and possibly come back and work at places like Bell Labs. So Bell Labs was really a pioneer. It was the first industrial organization to actually have a program of this type to try to improve diversity. And so I went on to get a PhD. I did my thesis work at Bell Labs, but the university I was at City College of New York, and my advisor there was Professor Robert Alfano. So two thesis advisors, Bob Alfano and Dave Austin, but did all the work at Bell Labs. Now, some of you that have been around for a while may recognize this as a very high power neodymium glass laser. And what I'm actually doing here is using a Kerr cell as a way of picking out a pulse from a mode-lock train. So this was a glass laser that was available at that time at Bell Labs. Cutting my teeth on a fairly large laser. So actually that summer was so good, and it really changed my life. This is one of those diversity programs affirmative action program, where it really benefited me. It helped me mold my career. And that first summer, I actually wrote my first technical paper with my advisor, Dave Austin, in the IEEE Journal of Quantum Electronics. And so this was it for me. I knew what I wanted to do. I wanted to do optics, and I wanted to work at Bell Labs. And fortunately, I was able to do that once I finished my PhD. So these programs do work. They've inspired me, and that's got me involved in trying to actually bring more people along. So here is a picture of a Gordon Research Conference. This is 1981, the Gordon Research Conference on nonlinear optics and lasers. This was probably one of my very first conferences. My advisor, Dave Austin, was the chair of the conference. And you'll see that for those that have been in this field will note that the big players in optics were all here. This is Steve Chu, before he got his Nobel Prize, and is now head of the Department of Energy. Back here is Nico Bloombergen, another person about to get a Nobel Prize at Harvard. Here's Kumar Patel, invented the CO2 laser. There's just so many folks in here. Peter Moulton, invented the titanium-doped sapphire laser. Eric Gippert from MIT. Short pulses. Chuck Schenck, head of Lawrence Berkeley Labs at one point. He actually hired me at Bell Laboratory. He was my department head. But notice also in this really wonderful picture is that there are only two people of color. Myself, Deborah Jackson. We happened to be both colleagues. We were both contemporaries. She did her PhD at Stanford under Art Shallow, and who was a Nobel Prize winner herself at Stanford. But we were both part of the Bell Labs program. Deborah is now a program manager at the National Science Foundation. But I just show you this because this was quite an eye-opener that indeed we need to do more. Even at this time, much more needs to be done to make the field more inclusive. But this was a wonderful conference. I mean, everybody that in the optics field was here. So I'm going to show one statistical plot. And this is from the American Institute of Physics with some very appalling statistics. There are 189 PhD granting physics departments in the US, 5,200 full-time equivalent physics faculty. In 2000, there were 38 African-American faculty, and that increased to a whopping 66 African-American faculty in the United States. So this made me realize that I was myself was an endangered species. And here, Hispanic faculty, 81 and now 230 Hispanic faculty in these PhD granting institutions. So the number of Native American faculty members was even too small to count. They didn't even have a statistic on that. So 87 of these PhD granting physics departments had neither African American nor Hispanic faculty. There's nearly half of them. So things really need to move forward. And this, again, this is I promise, the only statistics I will show with the time I have left. So one of the things that people say is, well, I can't find any minorities out there to recruit. Well, here's an example of the National Society of Black Physicists meeting. This was 1994 at Georgia Tech. And so what you have to do is you have to go and look. You have to go and beat the bushes and mingle. And I managed to recruit a number of students to my research group by attending these meetings. And I've attended ever since I was a graduate student. And there's one more recent one in 2001. This was at Stanford. 409 students and professional physicists attended this conference. So again, the students are out there, they're interested. You have to do some work. Now, I left Bell Laboratories in 1995 to join New Jersey Institute of Technology as chair of the physics department. And these were my first 3 students who happened to be Black and Latino, who are now PhDs. Hernando Garcia was my first student. He's now a professor at Southern Illinois University. Elaine Lelaine is Ferdinand Aguama graduated. Elaine is a research associate. She decided to stay with me and working in my laboratory, actually running my ultrafast laboratory. And so they were all finished. Now here are some observations that I've learned over the years. Due to a typically subcritical mass of underrepresented minority and women students, a supportive and nurturing environment is usually very important for retention. I have found that underrepresented minority and women students gravitate towards research groups led by underrepresented minorities and women, and I am very fortunate that I have a 100% retention rate in my group. In the case of foreign students, there is typically a critical mass of students who will create a supportive environment, whether or not the advisor or department provides one. One rarely hears about issues of retention in the case of foreign students. However, there appears to be a correlation between foreign students and foreign faculty. And this was my personal observance when I was at Bell Labs. Though initially I was skeptical of the concept of a role model when I left AT&T Bell Labs to join academia, because I met with lots of minority students, but they were attracted to Bell Labs, and I didn't see the correlation there. But I did when I left and went to academia. I discovered that I attracted underrepresented minorities to my research group in a department that had no such students before my arrival. My second PhD student, Dr. Elaine Lane, was the only African American woman to receive a PhD in physics in 2003 in the entire country. And so numbers like 1 and 2 are typical, unfortunately. I now believe that this concept of a role model actually works for both foreign and domestic students, and of course women. It is therefore imperative to increase the number of underrepresented minority and women faculty to have an impact upon the diversity of science and engineering graduates and graduate students. I've also found that within an academic department, many students would segregate themselves along racial, ethnic, and foreign status lines unless the department made a concerted effort to provide a forum for these students. And I learned this when I was chair of the department at NJIT, and noticed that the Chinese students segregated themselves from the white students and the few minority students that were there. And what I did was I found space for all the groups to get together and to mingle and to actually work together and to study for qualifying exams together, and that broke that barrier. So yeah, providing an environment where you don't have the segregation is important to having this work. Now, I'm also part of NSF Engineering Research Center, ERC, and they have annual meetings. And the ERCs provide a focus across academic departments and schools which fosters cooperation among foreign and domestic students. Now, my group at this time was largely Black and Hispanic, and Professor Faustin Choa's group was largely Chinese. MERTH is our Engineering Research Center, Mid-Infrared Technology for Health and the Environment. Has brought our two research groups together to work on quantum cascade lasers. So, and we have a really strong collaboration between our groups. And we work very well and closely together. And this Engineering Research Center may have been the spark that got our two groups to actually work together. So my students and Professor Cho's students work very closely together, and they're in my lab all the time, and we're collaborating, we're doing research, we're publishing papers and interacting, and I think this is very important. So photonics has proven to be a wonderful visual medium to attract and fascinate young minds into science and engineering, and it caught my attention some 35 years ago as a young scientist coming out of Brooklyn. Here's a picture of my group a couple of years ago, in which we are working over a hot laptop trying to write a proposal for NSF. So these are members of my group, and we're working together, putting our ideas together for one of these difficult NSF proposals, as many of you know, how much work they require. Now, Robinson Queese, a Latino student at NJIT, came to my lab as an undergraduate and started working on mode-locked lasers and nonlinear optics. And then he decided to join my group to go to pursue a PhD. And when I left NJIT to go to the University of Maryland to head this photonics center, he decided to come with me, which I was really surprised at. And we helped me build my new lab from scratch. And he graduated with his PhD in applied physics this past December. And he'll be one of no more than 10 Hispanic Americans getting a PhD in physics. And that's typically, those are the low numbers. And he is now chief scientist at a mid-infrared fiber company, doing quite well. This is a picture of two of my students. The other student, Dr. Raymond Edzia, received his PhD a few months ago, and also in applied physics, and is now doing a postdoc. This is another student of mine, Victor Torres, who is well on his way towards getting his PhD, and he is in one of my student training labs, in which every student that works in my group has to build what we call a nonlinear optical autocorrelator from scratch to measure picosecond pulses. And so this is, what he's doing is taking a neodymium vanadate laser that's double to the green, and he's actually building an autocorrelator so he can measure the 7 picosecond pulses. So you have to do this first before you move up into my big laboratory. And this gives you an idea of how to work with lasers, how to set up mirrors, I mean the whole 9 yards. And it's interesting, the students compete with each other to see who can build it faster. But one has to do this in order to work in my lab, and they all know that that's the ritual to be part of my group. And now he is working on ultra-fast nonlinear optical switching and carbon nanotubes for his PhD. So here is a picture of my group, which is quite diverse, the ultra-fast optics and optoelectronics group. And we've got a little mixture of everybody in here, and this is the way I like it. It's working well. We are like a family here. And I also get the pleasure of working with middle school students typically every summer, and these are our future optical physicists and engineers. And I'm going to end with this photo, which is one of the proudest moments for me in my career. It was actually being elected Vice President of the Optical Society of America and joining this august group of past presidents. So I was president of the OSA in 2002, and it was quite gratifying to have the membership nominate and eventually elect me into this group. So I will stop there. And I'd like to entertain any questions. I think we have time for questions.
Anthony, do you get much support from your administration, your institution, in your efforts to attract minorities?
Yes, I do. Turns out that the president of my institution is Freeman Rabowski, is well known for a group of scholars called the Meyerhoff Scholars, and they are producing. They are graduating students in science and engineering, and particularly the medical field, at really large rates, and many of these students go on to PhDs, PhD, MD, PhDs, and so I do get support. And so we have a really good effort at UMBC in the biological sciences and chemistry, and so the president is hoping that I will kind of spearhead something more of that in physical sciences and engineering. So I have really good support. Yes?
Anthony, could you connect for us your applications of those quantum cascade lasers in medicine? What are you doing?
Okay, yes, this is a very good question. It turns out that one of the core technologies for our Engineering Research Center is breath analysis. One of the things that we're trying to do with this MERTH Center is improve that. Right now, in the case of breath analysis, one breathes into a bag, and that bag goes off to a lab, and they do mass spectrometry, and they try to determine what is the contents of the breath, and that takes time. And for example, one of the trace gases that we're interested in is ammonia, and it turns out that ammonia is a good indicator of health or non-health in liver and kidney function. And so what you do is by measuring the amount of ammonia in your breath, you can say something about how healthy your kidney or liver is. And what we'd like to do is take advantage of some physics, and that is of some vibrational rotational spectroscopy. It turns out that ammonia has absorption in the visible and in the near IR, but when you go to the mid-infrared, around 8 to 9 microns, the absorption at those wavelengths is 3 orders of magnitude higher than, say, 1.5 microns. And so by moving to the mid-IR, you enhance the sensitivity of your ability to detect trace amounts of these gases by orders of magnitude. And so it turns out a quantum cascade laser is a new type of semiconductor laser that operates in the mid-infrared. That's its whole purpose. And so we're trying to make sensors and lasers so that we can have a handheld device about the size of a cell phone that an individual could breathe into and get an immediate reaction as to how many parts per million or trillion that you need, and then immediately do something about it, as opposed to wait a couple of days and you might not be around to know that you have a problem. And so this is why the NSF decided to fund this engineering research center. So we're looking at all types of trace gases that actually have enhanced absorption in the mid-infrared range. And quantum cascade lasers are leading that effort.